For decades, scientists and astronomers considered that it would be impossible to ever obtain an image of a black hole. After all, these are objects so massive, not even light can escape them. So how do you get an image of a black hole that swallows up all the light around it? The answer is to figure out a way to capture the silhouette of the object, set against the glowing plasma that is being sucked in. Many think black holes first originated with Albert Einstein and his fellow physicist Carl Schwarzschild, but actually the idea of the existence of black holes was first posited by an 18th century rector named John Michel, who theorized there could be stars so massive that the escape velocity of the light would be overpowered by the gravitational pull of the star, pulling whatever light trying to escape back into itself. It was in 2000 when an astronomer named Dimitrios Saltis of the University of Arizona and his team came up with a way to view the event horizon of a black hole. But of course, there was a problem. Getting pictures of the planets in our own solar system is one thing, but getting an image of a black hole in a completely different galaxy is something else. The known black holes which were optioned for viewing were very far away, thus appearing extremely small from where we are here on Earth. Due to a phenomenon known as diffraction, there are limits to the size of objects we can see. Basically, to see something smaller and smaller, we need to make our telescopes bigger and bigger. It was believed that there would need to be a telescope the size of Earth to achieve an image of a black hole, so they got to work on figuring it out. Telescopes of all sizes and types are used to see distant objects. The larger the diameter or aperture of the telescope, the greater the ability to gather light and gain resolution. This gets increasingly difficult when the object you're trying to see is in a galaxy far, far away. Our own galaxy, the Milky Way, is said to be home to a few black holes. However, there's one called Sagittarius A star in the center of our own galaxy, and much closer to home. The problem with this is that there is a lot of stuff in between us and Sagittarius A star. There's thousands of light years of gas, dust, debris, planets, and other stars in the way, so seeing past all that wasn't the best option for where we should first set our telescopes. Instead, scientists determined the first target should be the supermassive black hole in the center of M87 or Messier 87. This gargantuan elliptical galaxy is about 53 million light-years away, or 318 quintillion miles, and resides in a neighborhood of galaxies called the Virgo cluster, also home to several trillion stars. It's substantially more massive than our own Sagittarius A star, which contains about 4 million solar masses. In contrast, M87 star contains about 6.5 billion solar masses. By the way, a solar mass is equivalent to the mass of our Sun, and a black hole is given an asterisk after the name of the location but pronounced star instead of asterisk. In this case, M87 star. So this Event Horizon Telescope was formed. It's not your average telescope, however. It's actually composed of 8 sites around the world, with more being added to this day. Each telescope must be highly synchronized with the others to within a fraction of a millimeter, using an atomic clock locked onto a GPS time standard. This degree of precision makes the EHT capable of resolving objects about 4,000 times better than the Hubble Space Telescope. They still had to wait for all the locations to experience the best cloudless weather, and they also had to come up with a way to decipher the information coming in. A 29-year-old computer scientist named Katie Bouman led development of a computer program that made this breakthrough image a possibility. She started making the algorithm years into the process while she was a graduate student at Massachusetts Institute of Technology. Bouman and her team said the algorithm converted telescopic data into the historic photo we now see. She spearheaded a testing process whereby multiple algorithms with different assumptions built into them attempted to recover a photo from the data. As each telescope acquired data from the target black hole, the digitized data and timestamp were recorded on computer disk media. Gathering data for 4 days around the world gave the team a huge amount of data to process. It ended up being about 5 petabytes of data, and this had to be transported to a central location since the internet at that time wasn't able to handle that amount of data transfer. At this location, data from all 8 sites were synchronized using the timestamps and combined to create a composite set of images revealing the never-before-seen silhouette of M87 star's event horizon. The EHT image shows the glowing plasma matter where electrons have been stripped from their atoms by this intense friction surrounding the black hole, with the shadow at the center revealing the shape and size of the event horizon itself. This gravitational influence of the black hole is the way we're able to see it. So we're not seeing the black hole itself, just its silhouette set against the glowing plasma being drawn into it. The asymmetrical shape of the matter shows both the way plasma swirls around the event horizon and how the gravitational distortion of space-time affects the path of the light emitted by the material. The shape confirms the prediction set up by Einstein's theory of general relativity. Some might think that this black hole is rather small. When you hear the terms singularity and hole, one might think that everything is being pulled into this tiny little area, but the black hole area measures about 40 billion kilometers across, or 3 million times the size of Earth. The entire disk you see in the image is about the size of our solar system. You may now know that since the first imaging of M87 star, the team was able to also image the black hole at the center of our own galaxy in another historic first. Learning about mysterious structures in the universe provides great insight into physics and allows us to test observations, methods, and theories. One of the direct results from this imaging project is a more direct calculation of a black hole's mass and a more accurate estimation of a black hole's accretion disk. When Apollo 8 turned around and took a picture of Earth, there was this wonderful moment of seeing a picture we had never seen before. It wasn't just a picture of ourselves, but a picture of how far we've come. The image of M87 star should surely stand the test of time and become a benchmark of how far humanity can go when their ideas, theories, and imagination is put to the test, pushed beyond its limits, only to create a new flag in the sand to symbolize where we've been and how much further we can go.